Hi, everybody. How are you doing? I'm okay. I made it through today. Thank you for asking. But yeah, Monday is usually pretty busy. Everybody gets back to work and tons of meetings and emails. I had a class earlier, so it's good to know that you're doing well. So we'll wait a few minutes. While we wait, please check out our assignment for today and the notes. We will work on sets this week. Did you have a good weekend? Some relaxing time? Work and make money? I work mostly through the weekends too, so. But I'm looking forward to spring break. I don't know about you, but mid-April, I'm excited about that. Welcome. We're waiting a few more minutes, so. Probably gonna try to relax. If it's warmer, I would probably swim and hang out with my dogs. They love it now that I'm home all the time. So, but yeah, work on curriculum sometime later on, just get preparation for. Also, fall semester schedule is going to be due. But, well, I hope you are able to enjoy spring break that's going to come up in mid-April. Yeah, I know. So hopefully after all of this, we're able to travel a little bit more or, take small vacation, go camping or do something fun. I know some campsites start to open up now. So I know resorts like ski resorts are opening too. So, okay, we'll start in a minute. If you just join us, please check out our notes and our assignments. We'll do this together, complete the assignments for today. And then on Wednesday, we'll do the lab with C++, like what we did before, but a little longer than last time. This class is pretty easy, so. Okay. Check out Chapter 7 notes and assignment, please. Let me close my Python class materials. So really brief announcement. I posted an extra credit opportunity if you have time and if you're not working or attending another class, you're welcome to join us. In the winter, I submitted for the IREX, who is a sponsor for the UN solutions. And with that, we work with schools in different part of the world to create projects to solve one of the missions. The missions that we're going to go for is clean water for our local community and for the community in Iraq. So we are 3D printing water filter and we are building sensors with Arduino. I don't know if you know, but when I started teaching at Moreno Valley, I incorporate Arduino as part of my programming class. And it was really fun because they get to create like sensing things. And I hope to do that again in some of these projects. So if you have time, you're welcome to join us and learn something new and work with students internationally. We're working with the school in Iraq, and hopefully we'll be able to have some design thinking and build some really cool solutions. So, all right, it's 6:01. So I'm gonna go ahead and begin. If you just join us, we are covering chapter 7 today. We're gonna jump a couple of chapters. We're gonna come back to 5. 4 is kind of pretty basic. So I'm gonna touch on some of the concept later on, but we're gonna emphasize on the next area, which is we're gonna work with sets. So I'm going to go ahead and go into screen share. If you have any questions, you can type it in the chat or you can unmute and ask. Okay. And we do have another extra credit opportunity outside of the global solutions one, which is going to come up in the next week. So this week we are going to work with sets. I will post the recording in the module itself for both days. We are going to work on our in-class assignment now. You do have a homework assignment, so keep an eye out for that. This homework assignment is aimed to help you prepare for our quiz next week. We will have a multiple choice quiz, which covers the concept that we've been working on, right? Number representations, and then a little bit of operators, and then going into the set. So the first few chapters, we're going to have our first quiz. I normally do a quiz review game where you get a chance to score really high and be able to win an e-gift card. So I will post that next week along with the quiz. So make sure that we take time to do the homework this week. It's going to be available for a month, but the due date is going to be on March 7th. So if you click on the notes, you can download the notes and you can click the assignments to download the assignments. So in the notes, it begins with talking about, sorry, I'm in the wrong one, about sets. And if we're looking at natural number, that would be a set. Or if we're looking at integers, so in C++, we would have the data type int to store integers, which is whole numbers like 2, 3, 4, 500. And then you saw last week that we can use unsigned int as part of C++. So that will be positive integers only. And then you would have signed int for negative integers. We will also work with rational numbers. And for mathematical theories, you would touch on real numbers. So a set, think of a set as a container, right? And this week we're going to use set STL. We're going to talk about sets. So we would see that for our notation, when we write out a set, we would use the curly brackets or the braces to include the elements in the set. And the elements in the set doesn't have to be numbers. We can have a set of characters, right? A, B, C, D, E, F, G. We can have a set of vowels. We can have a set of nibbles, which are 4 bits in binary. We can have a set of strings. So a set, basically, it is a container, and inside that container, we can include elements, values, and we would enclose it with the curly brackets. So when we write out the notations, we would say that, let's say a set is a set S, and X is an element of S, so we would say X, E, S. So that means that X is an element within S, within the set. And X could be anything, right? In this case, it's just an identifier or a name called X, but it could be a value, and that it could be a variable that holds value. So in this case, your X is an element of a set, and we would indicate it using this E symbol. Now, when X is not an element of a set, we would write it as X with an E with a strike. That means it's not an element of S. Okay, so just to familiarize yourself with some of the notation, you will be asked on quiz and exam how to utilize this notation and what they mean. Now, in some cases, you would have two sets that are equal. And sets is not usually in programming language. We would know that it doesn't have to be an ordered set, right? That doesn't mean going from small to large, but each of the element has to be unique. So we can have one set that's going to contain A, B, C, and it would be equal to another set that's going to contain the same elements, which is B, C, A, or C, B, A. So when you see element values are the same, then you can say that they are equal as sets. And in some cases, when we work with sets, we would see a finite number of elements. Let's say that I would have a set of all the characters in the alphabet. That will be a finite number of elements. And in other cases, we would have infinite number of elements in a set. So when we say natural numbers, that can go on forever, right? Or we can have a set that would be endless. So in that case, it will be infinite. Now, in our sets, what very similar to other containers that you see in C++, like array or vector, right? You in like an array, you would have a number of elements that you would have in that array. So let's say that we have an array that has 4 elements. So when you declare that array, you would put the 4 inside the square brace to indicate that that array contains 4 elements. The set has what's called cardinality. And cardinality represents the length of the set or the number of elements inside that set. So the example that we see here on the first page, we have S it's going to contain 1, 2, 5, and 7. That means that when we count up the number of elements in that set, we can say that the cardinality of S is 4. And the way that you represent the cardinality is like this, okay? You would use a pipe symbol, S, and then another pipe. So that means that it contains 4 elements. So in this case, this would be a finite set, right? We only have 4 elements. I mentioned before that we can have infinite sets, and it would contain infinite number of elements. And other cases, we also know that set can be an empty set, right? So let's think about a container in programming language, a place where we would store the element. Then some container we can have like an array. We can have an array that's dynamic that contains no elements yet, right? We can declare that. And then later on, we can initialize the element for that particular container. Similar to that concept, we can have an empty set and it would be indicated with the curly brace like this, or a 0 with a strike through. That means that it doesn't have any elements, okay? So in the first question, it asks you to denote a set, okay? So if we're saying that A is an element of B, we can say AEB. And you're welcome to copy and paste the symbol so that way you can have the exact symbol if you like, or you can type out the E. Some of the symbol, right, like this one looks like a C, but the C with the underline, you know, if you can't find it in your font, you can copy and paste the symbol. So for number 1, we simply say that A is an element of B, okay? And sometimes we would have a subset within a larger set, right? You would have a group of numbers that would be part of a larger group of numbers. So in this case, we would have an element is part of the B set. For 2, same thing. We would denote V is an element of T, okay? So we would say VET. V is an element of T. It's part of set T. Any questions so far? Now, okay, I see a chat question. Okay, nope, just a comment. Okay, we're good. All right. So for number 3, we're going to look at the set P, and P contains 4, 9, 24, 60, and 105. And keep in mind that when you're using like set STL, which is the library for C++, right? The element values have to be unique. And in Python, when we use the set, like the non-frozen set, if you took my class for Python, you remember this, right? It can be unordered, right? It doesn't have to be going from small to large, large to small, but they have to be unique in value, okay? So for P set, we're going to count up the number of elements, and that's going to give us the cardinality, which is the number of elements in set P. So you would say the cardinality of P is 5, okay? And this is important to note because when you start to compare set, what you will see is that first we have to start out with looking at the number of elements in that set. So if I have set P it has 5 for cardinality, and I have another set called set Q, and it has 7 for cardinality, they're definitely not equal, right? Because Q would, or another set would be larger because it has 7 elements compared to set P. Question?
Yes. How do you get the element of symbol?
If you, in the assignments, I give you a table, you can simply copy and paste the symbol in.
Okay, thank you.
You're welcome.
Would we have something like that on our test where we could copy and paste it?
No, your test is multiple choice.
Oh, okay.
So yeah, so the question might ask you, right? Like which of the following option would denote, X is an element of Z, let's just say, and then you would have to pick the one that's right.
Okay, thanks.
You're welcome. Okay, so cardinality simply is a way to count up, right, the elements or the length of that set. So I have a question. So duplicate element would not affect the cardinality. So what happens is in our case, when we use C++, right, or even C-based language, you will see that when you try to enter or when you're trying to store the duplicate values, it would only store 1. Okay, so let's say if I have 2 number 4, when I initialize that set, it's either going to give me an error or it's only going to record that one value one time. Okay, and same thing with Python. So Thank you, Jason, for clarifying that. Very good. Okay. And so now when we look at the next question, number 4, we would see that for the cardinality of Q, we simply count up the number of elements, just like what we did with 3. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So in this case, our cardinality is 9 for set Q. So Q has a cardinality of 9. So for 5, as we saw in the notes, we would have a notation for an empty set F. So how do we indicate that F doesn't contain any elements? You can simply say F and then use the curly brackets. Or we can say F with the 0 with the strike through. So when you see this, you would know that it is an empty set. And to start any container, you know that the system starts with an empty set. And as you assign value for the elements, it's going to put that into that container. So the initial part is that it has to establish that container with nothing in it. And then as the developer, the programmer initialize the value. And even in decoration, right, you would say this is the container and then these are the elements. Then the size of that set is going to give us a cardinality. And when you initialize the value, it's going to take that empty container and it's going to fill it with the elements. So think about that process because that's going to help us looking through some of the things down the line. Any question? Okay. All right, next we're going to compare the set. Okay, so earlier we said that if two sets contain the same number of elements and the same element values, they are equal. And notice that when you look at number 6, you would see that they are not in any order, right? I can have 11, 99, 44. So it's just non-ordered container. But what you need to do is first, you need to look at the number of elements or the cardinality of each set to see if they are the same. So in set X, I have 1, 2, 3, 4, 5. So X cardinality is 5. And then I also count up the Y, the number of elements for Y, and that's also 5. So 5 check off for the cardinality. Then I can look at the values to see if it matches up. So I have 11 in both sets. I have 99 in both sets. I have 44 in both sets. I have 33 in both sets. And I have 77 in both sets. So therefore, they are equal because the elements are exactly the same in values. So we can say that set X is equal to Y because they contain the same elements and have the same cardinality. Any question?
So if one number was off, it wouldn't be equal to?
No, yes. So to answer your question, if I have a 78 here, it would not be equal to Y because 78 is different than 77.
Okay.
Or if you have higher number of elements or cardinality, then it wouldn't be equal. Okay. Okay. Any questions so far outside of this? Okay, so let's look at number 7. It's easy. So it asks you to determine if A is equal to B and C. So we need to look at set A and set B and set C. So the first thing that we need to check is we need to check the number of elements in set A compared to set B and C. So A has 2, 4, 6, 7 elements, so its cardinality is 7. B has 1, 2, 3, 4, 5, 6. So 6 elements in B. And for C, it has 2, 4, 6, 7. It also has 7. So it's possible, right, that we have A and C equal. We know definitely that B is not equal to A or C because it has less elements. Then what we need to do next is we need to look at the values of the elements to see if they match up. So they both have -2, they both have 67, right? They both have 23, they both have 91, they both have 10. But C has 4 and A doesn't. And C has 55 and A has 55 as well. So the difference is this one, 4, right? While A has 82, which is different than C. So based on that, we can conclude that A is not equal to B or C, right? So A is not equal to B and B is not equal to C because A contains more elements than B and C also contains more element than B. And when we compare A and C, C contains different element values than A and B. So the approach is the same as we did for number 6, but in this case, we have 3 sets instead of 2. We check the cardinality and we check the values within that set to see if they are exactly the same. Any question? Okay, so with that, we're going to switch back to the notes and we are going to cover additional concepts. So here it shows how you would be able to read the notation, right? So in this example on the bottom of or on page 1, you have set S and it tells you the first part right here, it tells you about that set. It tells you that X, which is an element of S, it's also an element of real numbers. And X squared plus 4X plus C is equal to 0. So when we set C is equal to 0, we plug that in, right? Then you have -4 and 0 for S. When you simply plug the 0 in, you solve for X, X would be -4 or 0. And then if you plug in C is 4, then you only have -2 in set S. And when you plug in 6 for C, you have an empty set. Okay. So in this case, we would use algebraic expression or the equation that's given to us to be able to solve for the values that would be in S. Okay. Now in the set builder notation, the first part as you saw in the last example, that will be the condition of the element. Okay, so for example, let's say V is an element of S. It will tell you which set is that element belong to. And then it would follow that with the condition for V. So you would first say what set is that element part of, and then what condition, or usually an equation that we saw earlier, is the condition of V. And this is what we call the set builder notation. And you would put that enclosed in the curly brackets because it represents the set. Okay. Now, in the notes, the author tells you that sometimes you would use a pipe or the vertical bar, they call it, right? Or sometimes you would use the colon. So sometimes you would see the colon to indicate, to separate, right? What is that element and its condition. So some of the example is followed. You would look at this one and it tells you that X is an element of Z and absolute value of X is less than 5. So that could be these values, -4, -3, -2, -1, 0, 1, 2, 3, 4, because when you plug in -4 for X, it is less than 5, -3, it's less than 5, and so on. Okay, another example is this one. X is an element of Z, X squared is less than 10. So that means that X squared, when you plug in for X, it has to be -3 up to 3. So you can take a look at those examples and see how they would be able to use the set builder notation to represent the values that would be for that specific element or in that set. Okay, so any question with this? So with that said, we're going to look at number 8. It says provide the set builder notation for the following. For A, we have the set of R in T such that R is greater than 7, which is equal to 3, 7, 10, 14, and 17. So when we write that, we would say R is an element of T. So we say what kind of set that element belongs to first. Then we will follow it up with the condition for R. And in the question, it already tells you R is greater than 7. So we would say R is greater than 7 such that R can only be 10, 14, and 17, right? Because 7 is 7 and 3 is less than 7. So we eliminate those values and we can say that R is greater than 7 such that 10, 14, 17, and infinitely anything above 17 would be, that could be R. Yes, you need to include the closing curly brackets because it's a set. Okay. Then for 8b, it says that the set of integers such that y to the third or y cubed is greater than 7 from 4, 5, 6, 7, 8, 9, 10 all the way through 16. You're asking because there is one missing there. One missing where? In here, you mean? Eric? No, you're only gonna use one. So I have an opening curly brace right here. And, oh, okay, I see what you're saying. Yeah. So Eric pointed out that I need to do this. So thanks for catching that. Okay, so we have for B, we have a set of integers such that y to the third is greater than 7 from these values, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way through 16. So when we have the set builder notation, we would put y is an element of z. Z represents the integers. And the condition for y to the third is greater than 7. So if you put in the value for y with 4, you would 4 cubed is greater than 7. So all of these values would be true for the conditions of y cubed greater than 7. Okay, so we start with y is an element of the integers. And earlier in the notes, the first part, it tells you what those symbols are, right? And then we state the condition of y cubed. That's given to us, y cubed is greater than 7. For y are these values, which came from the statement. And we can test it, and that will be true for y cubed. Any questions? Okay. So that shows us how to use set builder notation. Make sure that you know how to do this. You might see this on quiz and exam. All right. So let's do C. C said that the set of natural numbers such that y squared is less than 100, given y is 3, 4, 5, 6, 7, 8, 9. Okay. So we can start with y is an element of natural numbers. It tells us natural numbers, so we can use the n there. And the condition is y squared is less than 100. So when we test the values for y, 3, 4, 5, 6, 7, 8, 9, when we square each number, the result is less than 100. So if we look at this, we would say that y is a subset, right? Because it could be these values of the natural number. Okay, so you can have, it could be an element of, or it could be a subset of a larger set. Question. Okay, let's solve for D. The set of S such that S is equal to 9y, where y is a natural number, 1, 3, 5, 7, and 9, or any positive odd integer. So we have a little bit more nested area here. We need to take a look at the pieces of it. We're saying that the set S is 9y and y is a natural number. So you can do it either way, okay? The first way like this, or this way, the second way, okay? So we could say S is the set S is 9y and y is an element of n. The first way that we learn is we would say y is an element of the natural number and S is 9y. So you can write it this way or this way. I personally feel that this is more clear when I read it because it shows, right? But in this case, because S is also a set, so we can state that S is a set and it is 9y. And y is an element of natural number. So either way is correct. Any question? Okay, so for the next part, we're going to touch on Venn diagram. And you probably have seen Venn diagram in different level of math courses, right? It could also be presented in programming classes or design. So in our case, when we're looking at sets and interpreting in Venn diagram, we can use pictures to illustrate sets and subsets or the diagram itself. So in Venn diagram, we can say that U contains all objects. That's the universe. U can be real numbers. It can be, you know, our country. It could be everybody in the world. It could be a specific population or a group of values. Now, since I'm using the textbook that's used with Northeastern University, right? The example that they show is that it could be all students at that school, or you can say all students in RCCD. So you would have the universe. And in the universe, we might have a set S. So let's say that if we're looking at the universe is California, we can look at the group of students in California that's in S. Or if we're looking at the universe as Moreno Valley, we can look at a certain population in Moreno Valley, like Hispanic students, African American students, right? So, or Asian students, Anglo-Saxon students. So different group can be represented as a subset of the universe, which encompasses, could be one or multiple sets. So here it shows you a single set on the Venn diagram. Now we can have two sets, A and B. So if we're looking at like Moreno Valley College is a universe, we can look at different types of faculty, right? Like here I am in CIS with my colleagues, and then group B might be mathematics faculty or biology faculty. So there's not overlap in our cases because I cannot teach biology, so I'm here in this group A, and biology faculty cannot teach computer science classes. They stay in group B. It's separated. And then we'll look at some overlap one where they have special skills, right? So in this diagram, you have two sets that are disjointed, okay? So in our assignment, it asks you to draw a Venn diagram that is disjointed, okay? You can use Microsoft Word if you're using Word to type it up. If you hand draw, that's fine with me, as long as you can distinguish what disjointed sets look like, right? They are separated. There's no overlapping. So to use Microsoft Word, just real quick, you can do insert, shapes at the top, and then to draw the universe, I would use the rectangle. So let me move this down here. Let's say, and stretch it out. And then you can color it if you want. You can change up the properties of it. Okay. And then if you wanted to add text to it, you right click and then do an add text. So I can say U for universe, and I can align it any way I want, like that. I tab it backspace and it line it to the left for me. Then I can put in another shape, insert, shape, and then I can use the oval and then just drag your mouse. And then again, we can add text to that shape, right? We can say P, and then I can add another shape, insert, shape. And if you wanted to color it, you can change the color through the ribbon. Okay. And then add text. We can call this one Q. And I'm going to need to enlarge this a little bit. Okay, you can just drag it from the edge there. So here we show that we have disjointed sets in the universe for our Venn diagram. So for the quiz and test, you will be given Venn diagram to look at, and you need to interpret that diagram. Any question? Okay, so the example shows you how sometimes you would have a diagram that shows subsets, okay? So here in this diagram below, we see that A is a subset of B, okay? So let's say that your immediate family is part of the larger family tree, okay? And your family is part of the people in the United States, Okay, so the universe is the group of people in United States. Here's A is your immediate family. And then distant relatives, including your family, is part of a larger family, B. So in some cases, you would have A, and this is how we use the subset notation. It's the C with the underline. So A is a subset of B. So A is part of B, and B is within the universe. Any question? So here, the statement is important to look at. It says that this means that every element of A is an element of B, right? So when you check the element values, when you look at A, they match with some of B. And there at least one element of B that is not in the element of A. So that means that cardinality of B in the Venn diagram we see here is higher than A. It would have some elements that is not in A. It's larger. Okay. So in this case, A is a proper subset of B. And those of you who want to take this and interpret it in Python, Python has built-in methods that would tell you to look at disjoint, right? You can use disjoint method. You can see how it's overlapping. And this is why, we would implement those methods for analysis purposes. So when you're looking at a group of data and how that is interpreted. So there's a lot of really cool mechanism that you see in some programming language that evaluate sets, okay, compare sets, looking at whether it's a subset, and you also have a subset method in Python for that. Okay. Any question? You're welcome. All right. So let's look at the set operations. And you see this in a lot of, C-based library language. You would see union, things like that would come forward, because ultimately these developers, they have to write the tools to get the analysis done, right? We can just have the definition of, we define the function and then let that function do all the work for us. We write it once. So when you're looking at this Venn diagram, you have some overlapping, A and B, okay? Now, set A has some overlapping with set B. There's some area here, and this one is like a union. So let's think of this as like two family, right? I have the first family and I have a second family. And these family join together because there's a marriage, right? It could be two parents having two sets of kids from the prior marriage. They join together now, their union. Through their union, we're looking at a larger family, right? So we have set A and set B. So the way we denote this is we would do a U for the union, and it tells you that X is an element of A or X is an element of B. Okay, and X could be here in the middle. Let's say that two parents have their own kids, got married, and then have together they have another child. That is X. Okay, so when we look at the values for this, you would have A is 1, 2, 3, 4, B is 2, 3, 4, 6, 7, 9, and C is 1, 2, 9. When we do a union of A and B, A union B, you combine the two small sets to be a larger set. Remember, we became a bigger family through the union, right? So we have 1, 2, 3, 4, 6, 7, 9. Then if we take C and we union it with set B, then we would have the values for B combined with the values for C, and we put it together as a larger set. Okay. And the same thing for A union C. So when you're looking at the union, you would take those values from the original sets and you combine them into a larger set as a product of the union. So now for any set union, empty set is a set. So if I have a set and I have an empty set and I combine it, it's still going to be the same original value as the original set that I have, because the empty set has nothing, right? So when we do a set union with the universe, it is the universe because it is within the universe, right? That set is a subset of the universe. Okay, so any question with union? All right, so let's see. Let's answer number 10. Determine if the following statements about Venn diagram is true or false. A, if R is a subset of S, R is included in S, or S includes in R, then every element of R is also an element of S. So if R is part of S, that means the element of R is part of a larger set S. So it's included in S. Or some of the elements of S would be included in R. Sure. So that's true. Okay, if you're not sure, draw it out on the diagram so you can see. For B, every element of G is an element of H, but there is at least one element of H that is not an element of G. We conclude G is not a proper set of H. So what I did was I wrote out an example so you can see. If we have G is 1, 2, 3, 4, which also exists in H, and H also have 4 and 5 because it is a larger set, right? So we know that at least one element of H that is not an element of G. Sure, we have 4 and 5. But in this case, because G is part of H, it is a proper subset. So this word made that entire group of statements false. Okay. We should say we conclude that G is a proper subset of H. We touched on that earlier. For C, we can say, it says if X is a subset of Y, but X is not equal to Y, it's true if Y is a larger set. So we can say that X is a subset of Y. So let's say X is 1, 2, 3, 4, 5. And Y is 1, 2, 3, 4, 5, 6. Is X equal to Y? No, right? It is a subset of Y, so it has less cardinality, less elements. So that statement is true. Okay. So if you're not sure, write out an example so you can see, or draw the diagram so you can see. That way it clears it up, because sometime on the test, it can be a little confusing, right? So true for C. Okay, let's do the union, which is 11. We have X is 10, 20, 30, 40, 50. Y is 30, 40, 50, 60, 70. And Z is 10, 50, 100, 200. We are going to do a union of X and Y. So we're going to take the values for the X set, combine with the value for the Y, and put it together as a larger set. So 10, 20, 30, 40, 50, 60, and 70. After that, we would repeat the same process for X union with Z. So take the values for X, 10 through 50, and we're gonna marry them to the Z. But remember earlier, Jason showed you in the chat that when you have the duplicate value, you only note it once, right? Set has to have unique value. So we don't type out 2 10s, okay? X and Z has 10. So it's only going to record 110 in that set. We are only going to write one time 110. And it both has 50. We're only going to note 150. Okay. So we ended up with 10, 20, 30, 40, 50, 100, and 200. Okay, we don't duplicate for set. And then we're going to do the same thing for Y union Z. So Y, we have 30, 40, 50, 60, 70. Z, we have 10, 50, 100, 200. We notice that 50 is the same with both sets, so it's only going to be included one time. So together we have 10, 30, 40, 50, 60, 70, 100, and 200 for Y union Z. I put it in order because I wanted to just keep track of the numbers, but sets are unordered. So for the sake of the exercise, if it's easier for you to type in order, so you know which number you put down, sure, you can put it in order. But you have to know that sets sometimes are unordered. So you can have 200 in the front, 10 in the middle, you know, as long as you don't repeat the number multiple times and you include all the numbers for the union. So in the next part, we're going to talk about intersection. Any question before we leave number 11? Okay, so expect these on the test and quizzes, okay? At least, you know, the first quiz for us, and then also some of this is going to come back also in the final exam. But I will hold a final exam review. So, okay. In the next part, it talks about intersection. So here, what you have is you have A intersect with B, and it says that X is an element of A and X is an element of B. So X is in the red area. So earlier I used an example that there are faculty that can teach programming, and then there's faculty that teaches math. And then in my case, I'm in the red because I can teach programming and math. Okay. There's some faculty that can teach Spanish, along with faculty that can teach psychology. And then if they're capable of being in both, they would be in the overlapping area. Okay. So when you look at the values in the sets, you have A is 1, 2, 3, 4, B is 2, 3, 4, 6, 7, 9, and C is 1, 2, 9. When you have the intersection, you're only going to identify the element values that's repeated in the sets. That's the same in both sets. Okay. So 2 is the same in A as it is in B. 3 is the same in A as it is in B. And 4, same thing. It's in A and in B. So we put those down as those values are in both sets. So they belong in the intersection, in the overlapping area of both of the sets. Okay. When we look at A and C, we can see that 1 and 2, 1 is in A, 1 is in C, 2 is in A, 2 is in C, right? So that's why 1 and 2 is noted there for the intersection. And then you can do the same thing for B intersect with C, 2 and 9, okay? 9 and 2, okay? Now, important to note, just like what we saw earlier with the union, for any a set that intersects with an empty set is an empty set. Okay, because empty contains nothing, and when it intersects with the set, it would be empty set. A set that intersects with the universe is a set, where universe is the universe, or U is the universe. When you have two sets that are disjointed, okay, two sets are disjointed if and only if A intersects with B is empty set. So if they intersect and it's an empty set, that means that they don't overlap. So they are disjointed. They are separated. Okay. Okay. So here it also talks about how we would look at the cardinality A union B. We would take the cardinality and we add it, and then we would subtract the intersection cardinality that would give us the output for A union B cardinality. So let's do this, and then we'll talk about principle of inclusion exclusion. And this principle is important because that's going to carry you through the permutation, probability, and all of that good stuff in counting. So for number 12, we're going to do a union of R and S for 12A. So R intersects with S for 12A. So we are going to look at the values in R that's the same in S. So we notice that there's 10 in both, 15 in both. So we note 10 and 15 as the intersection for both sets. For 12B, we're going to find the intersection between set S and set T. So S is 10, 15, 25, 35. T is 15, 25, 35, 45, and 60. We see that 15 is in both, 25 is in both, and 35 is in both. So we can note those as intersection for set S and set T. For 12C, again, repeat the same process for R and T. Look for the numbers that appears in both sets. So we can see that 15 appears in R and in T, and 60 appears in R and in T. The other ones don't, so we don't use those for intersection. So 15 and 60 for 12C. Okay, so make sure we know how to find the intersection for sets. And we simply look at the value that appears the same in all these sets that we're comparing. Question. All right. So now let's move forward and talk about inclusion and exclusion principle and going into complement. So earlier you saw the statement about how these two sets, A and B, if we're looking at the number of elements in A union B, to solve that, we would take the cardinality of A plus the cardinality of B subtracted by the intersection of A and B cardinality. Okay, so if you look at the exercise we just did, the intersection cardinality, okay, let's go back here. So the intersection cardinality of R intersect T, it will be 2, right? Because there are only 2 elements that are intersecting, which is 15 and 60. That's what they meant by that. Okay. So now it says that when we add up cardinality of A and cardinality of B, we have counted all the elements of A and all the elements of B, but we have counted the elements of A. Intersects with B twice. So that's why we have to subtract it, because they exist in both sets. So we must subtract the number to get the correct result. And that means that we include, right, all the elements from both sets, but we also need to exclude the ones that got counted twice. Any question? Okay. So here, right, last week or 2 weeks ago, we talked about complements and how to find the 2's complement, right? We knot it, we add the 1. So now we gotta look at from the perspective of Venn diagram and sets. So here it tells you that we are looking at the complement of set A. So in the notation, we see that X is an element of the universe and X is not an element of A. So if set A is the white area here, X could be anywhere outside of A in the universe. Okay. So this is the way that we would represent the complement, is with the line across at the top. So if we look at this example, we have A 1, 2, 3, 4, B 2, 3, 4, 6, 7, 9, C 1 to 9, and U is 0 through 9. So the complement of A is anything but A, right? So we put 0 because 0 doesn't exist in A. 5 doesn't have 5 in A. 6 not in A, 7 not in A, 8 not in A, and 9 not in A. So we would take whatever that's in the universe and not in A, that will be the complement of A. And the same thing for B. B has these numbers, so we look at the universe, 0, not in B, so we note that. 1, also not in B. 5, again, not in B, and 8, not in B. So you get the idea, right? So we look at the universe values, and if it's not in the set, it's a complement of that set. And lastly, the empty and the universal sets are related by the complement of the empty set, which is universe. The complement of the universe is the empty set. Any question? All right, let's do the next one together. So for 13, you're given X, Y, and Z. Okay, X has 20, 30, 40, 45. Y 25, 30, 40, 50, 55, 60. Z 30, 35, 50, 55, 65. And the universe 10, right, increment by 5 all the way to 80. I put the little c, which is easier for me to do, and I use the superscript for that. But if you wanted to put complement of X, or, you know, if you find the symbol for the line for top of the X, that's fine. So I just use the C to indicate that it is a complement. So for X, I use the universe set and I compare it to X. Anything that's in the universe and not in X, I would put. So for example, 10 is in the universe, but 10 is not in X, so I put 10. Same thing with 25. 20 is in X, so we don't put 20. We leave 20 out. Okay, so 25 is in the universe, not in X, so I put 25. 30, I skip because it's in the X set. 35, not in X, so put that. Okay, 40 and 45, we skip those because it's in X. Okay. Yes, U represents the universe. And so on. So you keep identifying the values that's in the universe, or U, but not in X, and that will be the complement of X. Okay, so when I go through, I have 50, I put 50 because it's not in X, 55, 60, 65, 70, 75, and 80 because X actually stopped at 45. Okay, so these values represent the values for the complement of X. Then I do the same thing for Y. So I notice that 10 and 20 is in the universe and not in Y. So those go into the complement of Y. Okay. I skip 25 because 25 is in Y, so we can't put that. Same thing with 30, we skip 30. 35, we can put. 40, we're gonna skip because 40 is in Y. And then we put 45, we're gonna skip 50 and 55 and 60. So then we're going to jump to 65 and above because y stops at 60. And with that, you need to do z on your own. So look at the values for z and the universe set or U set. If you find it in U and not in Z, you would put that for the complement of Z. Question? So make sure we do the last one, okay, which is Z. We only have a few more to go, so it should be fast and easy. All right, now we're going to take a look at the next part in our notes. We're going to look at difference. Okay, so we have set A and set B again in our Venn diagram, and both of these are part of the universe. And it tells us here that when you take A, subtract B, for that X is an element of A and X is not an element of B. So it's in the red area here, okay? That will be the difference between A and B. Okay, so earlier we looked at the overlapping, now we're going to look at the difference. What's in A and not in B, right? And then when they are together like this, when they're union like this, we have to look at the difference. So let's look at the example. We have A is 1, 2, 3, 4, B 2, 3, 4, 6, 7, 9, and C is 1, 2, 9. When we look at the difference from A to B, okay, evaluate the difference from A to B, not the other way around. That's the next one. So we look at 1, 2, 3, 4. What is in A and not in B? 1, right? Okay. What is in A and not in B? 1. Then we're going to evaluate the difference from B to A. What is in B and not in A? 6, 7, 9. So these value is because we evaluate what's in B and not in A. Okay. After that, we're going to evaluate what's in B and not in C. So we would have 3, 4, 6, 7. So when you look at B, B has this, but C doesn't have what? 3, 4, 6, and 7 from B. Okay. So when you look at the difference like this, it's important that you pay attention to what's subtracting. And that's going to be the evaluated set against the other set. Okay. And then we go in reverse. What's in C and not in B? Okay, C has 1, B doesn't. Okay, and we would repeat that for the other ones. Now, lastly, it says that for any set S, the set S, subtract an empty set, the difference between these are going to be the set S. When we take the set, subtract the universe, that would give us an empty set. Okay. Any question with this? All right. Let's work on the next question, number 14. So for number 14, I have A is 2, 4, 6, 8, and 10. B is 4, 5, 6, 7, 8. C is 1, 3, 5, 6, 7, 8, 9, and 11. We are going to determine the difference for A, B, and C. So we first are going to look at we're going to evaluate the difference from A to B. Okay? What is in A and not in B? So for question 14A, we have A minus B is equal to A has 2 and B does not. So we put a 2. And for A has 4, B also have 4, so we skip that. Okay. Now we don't put the number 5 because we're not evaluating the difference from B to A. It's the other way around. So we're going to use this set and we're going to try to find what is in this set and not in the other. Okay. So we cannot put the number 5 for the result. What about 8? 8 is in both. So we're going to not put 8. We're not going to put 7 either because we're not evaluating the difference from B to A. It's A to B. Then we get to number 10. 10 is in A and not in B, so we put 10. So the answer for 14A is 2 and 10 is the difference from A to B. Any question? All right. Next, we are going to evaluate the difference from B to C. Okay, B subtract C. So B has these values. C is a larger set. So we're going to start with number 4. 4 is in B and not in C, so we put 4. 5, no, it's the same with both. 6, same in both, so skip those. 7, also skip. 8, also skip. We leave 9 and 11 out because we're not evaluating the difference from C to B, it's the other way around. So 4 is the only one. You're subtracting from B. And we would repeat the same thing for 14C. We're going to find the difference from A to C. So A subtract C. So we got to evaluate these values, what's in here and not in C. We see that 2 is the first one. It's not in C, so we put 2. 4 is the next value, not in C, put 4. 6, we skip. No, because they're in both. It's in both. 8 is in both. 10 is in A and not in C, so we put 10. And we disregard the others because we're only evaluating from A to C. So 2, 4, 10 is your result. Question? And since we're on the difference, we're going to proceed to symmetric difference. All right. Okay, symmetric difference. So now we're going to look at the difference from both sets. Okay. Earlier, we ignored the second set as we evaluated from one set to the other set, right? The second set, some of the difference we ignore. In symmetric difference, we have to include all the differences from both sets. So it uses delta, okay? So A delta B. So the symmetric difference between A and B in that X is an element of A and X is not an element of B. We're gonna union that with X is an element of B and X is not an element of A. So X exists in the red area in our Venn diagram. Okay. So the example that we see here is A is 1, 2, 3, 4, B is 2, 3, 4, 6, 7, 9, and C is 1, 2, 9. So first we're going to look at the symmetric difference from A to B. Okay, so we see that A has 1 and B doesn't, so we put 1. 2 is in both, we skip. 3 is in both, we skip. 4 is in both, we skip. But wait, last time when it was only a difference, we just ignored the rest. Now in symmetric difference, we have to include the difference from the second set as well. 6, 7, and 9 needs to be included. Okay. And if you go in reverse, you would see it's the same thing. So symmetric difference from A to B and B to A is exactly the same. And then we'll try one more with B and C. So for B, we're going to evaluate symmetric difference between B and C. We have 2 in both, 3. We have 3 in B and not in C. So that's why we have 3 and also 1 in C and not in B. So 1, 3. 4 in B and not in the other. So 4. 6 in B, not in C, put 6. 7 in B, not in C, put 7. Okay. All right, so let's do the next one. Any question? So for 15, it asks you to find the symmetric difference for A, right? Question A, between D and E. Given D is 1, 3, 5, 6, 7, 9, and 11. E is 2, 4, 6, 7, and 10. So we'll start with number 1. 1 is in D and not in E. We put 1. 2 is in E, but not in D, we put 2. 3 in D, not in E, we put 3. 4 in E and not in D, we put 4. 5 in D, but not in E, we put 5. 6 in both, we skip. 7 in both, we skip. 9, it's in D, but not in E, we put 9. 10 in E, but not in D, we put 10. And 11 in D and not in E, we put 11. There you would have symmetric difference between A and E sets. So repeat the same step for E and F. So we find that E has 2, F doesn't, put 2. F has 3, E does not, put 3. 4 we skip because it's in both. 6 on E, but not in F, we put 6. 7 we skip because it's in both. 10 in E, but not in F, we put 10. And 12 in F and not in E, we put 12. So you have the symmetric difference between E and F there. After that, you need to solve for C, number 15C yourself. Symmetric difference between D and F. Okay, make sure you put the answer. Pretty easy, right? Any question? So make sure we can distinguish between finding the difference between the sets or amongst the sets that's different than finding the symmetric difference, right? Symmetric difference, we would include the differences in both sets, where if we find just difference, we only include the sets that's being evaluated from. Okay. Then we're going to get to the next part here. Here it shows you a little bit on symmetric difference. So in this chapter, power sets is going to be the hardest area, right? All the other stuff is pretty fun and easy with the Venn diagram and set comparison. So now we're going to touch on power sets. Okay. So given this example, if I have A as a set, the power set of A, which is indicated as P of A, is the set of all the subsets in A. So what we do is we take the value, all the elements of set A, and make it into smaller subsets. And that's going to give us the power set. So if A is 1 and 2, A contains element 1 and element 2. Okay. The power sets of A, we would start with, remember coming back to earlier, we talked about it starts with an empty set. Then we would break this into one element, which is 1 for number 1 here, and then a set of another one element, which is 2. Okay, After that, we would have one set that includes 1 and 2. Okay, so the easiest approach to this is first you start with an empty set, then you build the subset that has one element, then you build the subsets that have another element, which is 2 elements. And in the case where you have a larger set, you're going to keep growing until you have the full set again. And with that, we have the power sets. Okay. So when we look at the cardinality of the power set, that would be 2 to the power of A. Okay, we would take 2 and raise it to the power of A, given A is the number of elements in the set. So in this case, if you count up how many subsets is in the power sets, you have 1, 2, 3, and 4. So to check this theory, if you take 2, right, raise it to the A power, which is 2 to start with, 2 elements, you get 4. Okay. Okay. So let's look at this example below. So you have set S, you have A, B, C, D, right? So the first round, you have the empty set. That's the first round. Then we're going to break up all of these elements into individual single element subset. So subset with one element, you have A, B, C, D, single element subset. Then we would have 2 elements, AB, AC, AD, BC, BD, and CD. Then the next round, we would have 3 element subset, ABC, ABD, ACD, BCD. And then lastly, we have a 4 element set, ABCD. Okay, and we're done here because we started with the 4 elements. Okay, so the power sets of S are all of these combined, right? Written out like that. And if you count them up, you would have 2 to the 4th power because there are 4 elements, or 16 for cardinality of the power sets S. And this is going to lead us into permutation and probability perfectly, because you're going to look at the combinations in the subsets. All right, any question with this for power sets? And we're going to talk about Cartesian products. Okay, so let's do the power set for number 16. You got a little peek from earlier, right? The first part anyway. So we have the set S is 2, 3, 4. And we need to find the power sets of S and also its cardinality. So we would start with the empty set, 0 elements. That's the first round. The second round, we would have a single element subset, 2 and 3 and 4. Then next, we're going to do 2 element subsets, 2, 3, 2, 4, and 3, 4. Then after that, we would do a 3 element subsets, 2, 3, and 4. So if you count all of these subsets up, you should get the cardinality, or we can simply use the formula 2 to the power of n, where n is the number of elements in that set. So I would take 2, raise it to the third, I get 8. Question. All right. No question on 16 or power sets? Make sure we know how to do this. You might get a question on the test and quiz about power sets. Good. All right, good to know that you're doing okay. Next, we are going to cover the last part, which is the Cartesian products in the chapter. Okay, so after power sets, it goes into Cartesian products. So Cartesian products is a mathematical operation that returns a set or product set from multiplying the sets. Okay. So if you're looking at this, basically you're taking one set and you multiply it by the other sets. So we have x and y, where x and y is the element of R. Okay. It's because that way we can visualize it on the plane. So it will be drawn with the coordinates like that because it's an ordered pair for x and y. We would take the order pair and write it out. So 1, 2, and 2, 1 are not equal. But when we look at the sets for those, they are equal, but the pair, they do not equal because if you graph it, it's not. So the Cartesian product is named after René Descartes. So when we do this, we would be able to find the product of any two sets. So in this case, we're going to take set A, multiply it by set B. And we have x, y, where x is an element of A and y is an element of B. So let's take a look at the example first before we do the next exercise. You have A is 1, 2, 3, and B is AB. Okay. When you multiply A, set A, and set B, you would have the first pair, which is the first number, right, of that set with the first number of the second set. So 1A. And then we would take the first number, go to the second number for the second pair, 1B. And then 2A, second number, and then the first number of the second set, 2B. And then lastly, the third number, first, and then the third, second. So 3A and 3B. Okay. So when we multiply the A and B, we would have these pairs as the product, what we know as Cartesian product. So with the general cardinality of this, when we take two sets and multiply them, we would get the cardinality of the multiplication, the number of elements here, right, is going to be equal to the cardinality of A multiplied by the cardinality of B. So I have 3 times 2, that gives me 6. If you count it up, 1, 2, 3, 4, 5, 6. That's exactly the same. Okay. And you can apply this to many sets, not just 2, right? So in the case where we would have a triple AB times C, it's going to be similar, but we would then have to have a combinatorics of 3 ordered pair. And this is, if you're familiar with Python, right, and you learn about tuple, and this would apply to the triple tuple or the nth tuple components. Okay, question. Let's do the last one. Is it the last one? 17. Oh, we have 18. Yep, 2 more to go, and we're gonna get close to 8 o'clock, so that's okay. Pretty easy. So first, I am given T, 2 and 4. U is 6 and 8. U in this case is just another set, not the universe. W is 1 and 3. Okay. So what I'm going to do with this is I'm going to use Cartesian product to multiply out set T, set U, and set W. So we will start, sorry, with the other crazy color highlight. So we start with 2, and we start with 6, and we start with 1. Okay, so first number from each of the sets. So we have 2, 6, 1 for the first group. Okay, and then I'm going to move from the first number of the first 2 to the last number of the third. So 2, 6, 3. And then we're going to go first number, second number, and first number. So 2, 8, 1. Then we have 2, 8, 3. 2, 8, 3. So we finish out with the 2's there. Then we're going to switch over to 4, which is the second number of the first set. Then we're going to go 4, 6, 1. So second, first, and first. Second, second, and first. Okay. So we're going to do 4, 6, 3. 4, 8, 1. 4, 8, 1. And 4, 8, 3. Okay. So if we wanted to check the cardinality of this, which I didn't type previously. So if we have T times cardinality of U times the cardinality of W is equal to what? 2 times 2 times 2 is going to give you 6. Okay. Why is it 8? Oh, yeah. So because it's 3 by 2. I'm sorry. 8. So I'm lacking sleep today, so you gotta forgive me. I left my brain upstairs. Okay, 8. 2, this is 4 times 2 is 8. Okay, it's good because we're at the last one. questions?
Is it always forward? You always move forward, never back?
Yeah.
So I started with the first and then the first, and then we're gonna switch up the combination. But remember that in a set, there's no order. So it doesn't matter how you approach it as long as you have the differences in the group or the tuple at the end of the day. Okay. All right. Last one. So I have about a few more minutes, about 9 more minutes until the session ends. This class actually goes until 8:10, but I'm only going to hold you till about 8-ish. Okay. So here it explains a little bit more about Cartesian products. And it mentioned that Cartesian products is not commutative, right? Cartesian product is not associative. It doesn't, using the theory, we cannot prove that it's that. So now computer representation of the sets, this is going to help with the last one. Just like number sets can be represented with 0 and 1s. Okay, so the stuff that we learn for conversion and things, leave that outside the door today. Okay, it's just going to be on if it's present, which is 1, off if it's not there, then it's going to just be 0. Okay, don't think about conversion when you do this because it's going to confuse you. So when we look at the order of elements in the universe, we would use bit strings whose length is the cardinality of the universe to represent the subsets of U. Each position of the bit string corresponds with the element of the U. So if the element is present, it's just going to switch that to on, which is 1. So a 1 in some position means that the corresponding element is in the set, while the 0 means the element is not in the set. Okay? So if we're looking at this universe, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if all the elements are on, it's going to show as all ones, right? Because they are all present from the beginning to the end. Okay? But if we're looking at, if this is the universe where all of the elements are present, and if we're looking at another set that's in the universe, S, we saw that 0 is not present. It's going to leave the 0 because it's not there. So off. Okay. Then 1 is present, so we have a 1. A 2 is present, so we have a 2. Okay. 3 and 4, since we don't have 3 and 4 in the S, it's going to put a 0. 5, it's going to put a 1. 6, a 1. 7, a 1. 8, not there, 0, because 8 is absent there. And then 9 is present, it's going to put a 1. Okay, super simple. If we look at another set, it's going to go 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, like this. Any question? Now, if it needs to do a complement of a set, it will just do a bitwise complement of that set S. Okay, where we already talked about how we do the complement, we knot it. Okay, flip the bits. Okay, you ready to do the last one? Let's do the last one, last few minutes. So we have this universe, 0, through 9. Okay. And we wanted to represent set A in bits. So if we look at this, 0 is not in set A, so we're going to have 0, not there, it's absent here. 1, also not there. A 1, a 2, and a 2, it's there, so it turns on that bit. 3 on, so I'm going to highlight these as the yellow so you can see. And then 4, not present. 5, there. 6, not there. 7, not there. 8, not there. And 9 is there. Okay. Question. Okay, so I show you how to do A, do B, and C. Okay. And when you finish, save your work. You can submit it today, or you can wait a couple of days from now. Make sure you turn it in by Wednesday. And then on Wednesday, we're going to do a lab together. Type your name in the chat, please. If you have any question, you can stick around to ask questions if you wish. I'm going to stay on for a few more minutes and then have a wonderful night. I see you Wednesday. You're welcome. Any questions? No questions? Does 18C look like this? Let me look at 18C. Yes. Rashad, that's correct. You're welcome. Have a good night. Thank you. Eric, do you have any question for me? Okay, if you don't have any question, okay. Okay, all right, good. Well, have a safe night, okay? I'll see you Wednesday. Bye. Thank you.